projectile motion is parabolic. So what we need to do now is projection at an angle. All right. So we need to do projection at an angle, but there is something else I want to do before I do projection at an angle. So when we compare it, when we combine the two equations, all right, let me get my brush. All right, so when we combine the two equations, we got y was equal to, all right, so basically a, the constant a, and of course, x squared. So what I wanted to say about this, and of course, a is a constant that is equal to something else. What I wanted to say about this is this. All right, so you are going to be tested on this all the time. So if you have a ball and you first kick the ball horizontally, it's then going to bend under the influence of gravity. All right, so it's then going to bend under the influence of gravity. We said this last time, but this equation, when you combine both of them, all right, so when you combine the horizontal motion, x is equal to horizontal velocity times the time, and then the vertical motion, y is equal to a half gt squared. When you combine both equation, all right, you will get, all right, so let me just do it. Time is equal to x over uh. All right, so put that into another equation. I'll get g, instead of writing t, of course I'll write the half. Instead of writing t, I'll write x over u squared. So this is just a result we get from the last time. What we want to do is just to analyze this result. So I'll have gx squared over 2uh squared. All right, so this equation is very, very important for the projectile. All right, so this is what we want to explore. All right, so what we want to show you is this.
Okay.
For every single position, for every x position, so just draw my x. All right, so this is my x, just like a graph. So I'm going to use the same thing, y, like a graph. So for each of my x positions, I have a corresponding y position. So I can ask you to find the vertical height of the projectile using that formula at a particular position for x. Right? So that's the concept. That's,
Okay.
that's the importance of that formula. All right, so that's the importance of that formula. All right, so that's what I want to say about that. And then we'll move again. All right, so okay with this one, okay here.
Yes, sir.
All right. Next thing we want to do projection at an angle. All right, so we want to do projection at an angle. So right now, you have a projectile, all right, on a horizontal ground, and then we're going to fire it at this angle theta. So when we fire it at this angle theta, what's going to happen, of course, is going to reach a maximum height, and then it's going to fall back under the influence of gravity, right? The reason why it does that is because of gravity, right? This is something that we see every day. We know that gravity is acting on all objects. So if we fire an object at an angle like this, what's going to happen is going to reach a maximum height. And then after reaching a maximum height, it's going to fall back down to the ground. All right, so that's the concept. This projectile has a initial velocity u. Right now, there are two things that's happening. The projectile is moving horizontally, and at the same time, it's moving vertically. So, so I have a horizontal velocity and I have a vertical velocity. Right? So here I have a horizontal velocity. I have a vertical. So I have a horizontal velocity. I have a vertical velocity. Right? So that's my concept. What I want to do now is I'm going to analyze. What I'm going to do, I'm going to write down all the information we have for the vertical motion and all the information we'll have for the horizontal motion. So this is the next one. So projection at an angle now. We're going to talk about projection at an angle in details. So I'm going to use it in, all right? Okay, here, finish.
Yes, sir.
I'm going to write this back nonetheless because that was just kind of a little brief intro. Now, this is everything about projection at an angle. So I have an object. I'm going to fire it horizontally. So I'm going to draw this as neat as I can. All right, there are some things that I want. What is the concept? Projection at an angle. You see this angle here, theta, is the same angle right here, theta. All right. If I draw a line like this, yes, the motion is symmetrical about that line. So the motion So the motion is symmetrical. All right, so that's the concept. What does that mean? All right, so lots of important points. So the diagram is going to be crowded. So I'm going to just try. You see the rise time, you see the time that the ball will take to move from the point here A to the point here B is the same time it will take to move from B to C. That's what we mean by symmetrical. So the rise time is equal to the fall time. All right, so that's it. So the rise time is equal to the fall time. That is telling me that my motion is symmetrical. All right, once the object is moving under gravity. Rise time is the same as the fall time. The next thing, very important thing, is that the vertical motion of the ball, watch carefully, you see the vertical motion of the ball now, it leaves the ground, it goes all the way up, and it comes back down to the ground. So you see the vertical displacement. What do you think the displacement would be? All right, so the ball leaves the ground and it goes back to the ground. So this is the ball leaving the ground and goes all the way back to the ground. So the vertical displacement, what do you think the vertical displacement will be based on what we did in CXC? All right, no, don't be afraid to guess. I remember being at a conference, a STEM conference, and one of the important things about that was in the American culture, excuse me, sorry. In the American culture, they entertain a lot of trial and error. So students can just, think about something and never, ever, ever, ever be afraid to guess. Never, ever, ever be afraid to guess and get it wrong. There's a saying that Einstein used to say that a genius is the person who makes the most mistake. But the genius makes the most mistake in the shortest possible time. So because the person practice a lot, they make a lot of mistakes. So what they do is learn from the mistakes. So the person who don't say practice as much, there are gonna be some mistakes that they're gonna make, but they're gonna make it at a time when it's difficult to correct. So, so this is not, I'll say, a wrong, right or wrong, just a guess. I just wanted to see what you will guess. So you have the object right here on the ground, and you throw it up, it goes all the way up, and it comes back all the way back down to the ground.
Okay.
All right.
So basically, it would be you're displacing the object in a way where it goes up, but then it doesn't come back to the exact spot that it came from in the first place.
Well, yeah, it goes back to the exact same position. It's just because for ease of drawing it on paper, I kind of had to draw the position here a little bit offset. But yeah, so it goes up and comes back down in the same line.
So it only displaces upwards.
Yeah, so what I'm saying is there in terms of the total vertical displacement when the ball goes up and down. So what we need to remember is what displacement means, the definition of displacement. All right, so displacement, the simple thing, simple definition is a change in position. So if I define displacement as a change in position, then it means that if I throw an object up and then the object comes back to the same position, it means that there is no displacement. All right, so if I start at a point here A and I go all the way around the world, once I come back to that point A, my displacement is 0. So displacement and distance is different because the distance along the path, all of this measurement along the path is distance. But if I start at the point here A and I go all the way around and come back to the point A, I've not changed my position, so my displacement is 0.
So, sir, may I ask a question?
Yeah, you can go ahead.
Say, for example, you have that same, like the dot starts somewhere, it goes all around the world, but then it stopped right before where it started in the first place. So would the displacement be shorter than it going all around the world and
Yeah.
coming up short?
Yes, and let us discuss it a little bit more. Say I go all the way around the world and I stop at the point B, right? What's my displacement? My displacement would be a straight line to B.
Okay.
So displacement is distance moving a straight line. That is completely different from distance covered during the journey. Yeah, all right? You can see that? So that's the
Yes.
concept. All right, so that's the idea. So it's completely different from distance moving a straight line. Sorry, distance move along the path. So displacement is distance moving a straight line or a specific direction, because when we say specific, we mean that we're moving in a straight line. Specific means one, right?
Yes,
So
sir.
yeah, so it means one. So that's the concept. So what I'm saying here is that once we understand what the definition of displacement, and I say what would be the vertical displacement of the ball when it rises and then fall back to its original position, that displacement is 0. Right?
Yes, sir.
Yes. All right. So that's the simple thing. Nothing too tough. And there, I will show you the reason why you have to know that, because they will ask you to prove certain things, and it's gonna be simple things that you're gonna prove, but because they're gonna of course assume that you understand the definition of displacement. All right. They're gonna give you those things.
Okay.
Excuse me 1 second here.
Yes, sir.
Yeah. The vertical displacement is 0.
Okay.
All right. So that's the concept. So the vertical displacement is 0. All right, so we have said that the motion is symmetrical, very important. And of course, we can identify the maximum height of the projectile, very important. So we're ready to start. I'm going to analyze the vertical motion, and I'm going to analyze the horizontal motion separately. All right, so,
Okay.
so tell me when you're ready.
I'm ready now, sir.
Mhm.
I'm ready now, sir.
Ready? Ready? Hello?
I
You're
said
ready?
I'm ready now, sir.
Okay.
Yeah.
All right, so this is theta. every slant velocity can be split into two components. You're going to have a horizontal component, which I'm going to call UH. I'm going to have a vertical component, which I'm going to call UV. All right? So once it's moving along an angle like this, or along a slant, once I have a slant velocity, I can split it into two components. The horizontal component of the velocity is UH, and the vertical component of the velocity is UV. All right?
Yes, sir.
Yeah, so they say the vertical motion, so UV is going to be equal to sine theta. All right, so that's the vertical velocity. The horizontal velocity is going to be u cos theta. All right, and I can prove it. I can show you how I arrived at that. This is a right angle triangle, right? Yes.
Yes, sir.
Remember, vertical and horizontal meet at 90. So UV is opposite to the angle theta. So I can say the sine of the angle theta is equal to opposite. UV is opposite to the angle divided by the hypotenuse, which is U. If I cross multiply, 1 times UV will be UV, and U times sine theta will be U sine theta. All right, so that's how we arrived at this expression for vertical velocity. Same concept, UH is adjacent to this angle theta, so the cos of that angle theta is adjacent, UH over hypotenuse. Cross multiply 1 times UH, UH times cos theta, U cos theta. All right, so that's
Mm.
all right. So okay,
Yes,
okay so
sir.
far.
Yes, sir.
All your initial velocity, U sine theta. All right. While the projectile is moving up, your acceleration is negative. So it's going to be negative meters per second squared, meters per second velocity. And so we can write down some equations. At maximum height, what is happening at maximum height? The final velocity of projectile at maximum height is 0 meters per second. And we can talk about the time to reach maximum height. So if we use the equation V is equal to U plus AT for the vertical motion, at maximum height, V is equal to 0. My initial vertical velocity is U sine theta. So my acceleration going up is negative G, so I'll put that T. So therefore, one of the first equation that is good, the time to reach maximum height. All right, so let me back up a bit. Let me not just jump to right there. So let's just solve this. So I have 0 is equal to U sine theta minus GT. Let us carry the GT across. So I have GT is equal to U sine theta. So T, when I divide both sides, U sine theta over G. All right, very important formula. This is the time to reach maximum height. All right, so the time to reach maximum height depends, of course, on gravity. We're expecting that. So if gravity is pulling us hard, it's gonna, of course, take a longer time for us to reach all the way up. It's going to take a longer time for us to reach all the way up if gravity is pulling us hard. So that's the idea. Agreed? Agreed? So, all right. So, of course, we know that the flight time, the time to reach maximum height will be dependent on gravity, right? That's not surprising. Also, the time to reach maximum height should depend on the initial velocity of the object, right? And also, the time to reach maximum height depends on the angle. All right. So, if you fire the projectile at a horizontal angle, it's not gonna, yeah, all right, it's not gonna move vertically any at all. If you fire it at this angle, all right, that will affect the maximum height it will reach. All right, and of course, as you increase the angle until it reach vertical, so the angle affects the maximum height reach, and so it affects the time to reach maximum height. So this time is very important because when you're analyzing the motion, we are actually, let me tell you where we're at. We're actually here. So you see automatically, without even calculating again, I know automatically the total flight time. Because the time to rise is the same as the time to fall, right? So I know the total flight time. All right, so that's the concept. All right, so this is one important equation not to remember, all right, because you can always derive it. But of course, in projectile motion, the thing with projectile motion is that anything can be thrown at you. But the thing is, all the questions are set in Kate, they're a little bit standardized, but really and truly, projectile motion can come from any angle. So, good thing to know is, all right, the principles. So they'll ask you, how long would it take for a stone or a bullet to reach maximum height after it was fired at a particular angle? You would know that you would say, okay, I'm going to analyze the vertical motion, and at maximum height, my final vertical velocity at maximum height is 0. Remember, though your vertical velocity is 0, you still have a horizontal velocity. Agreed?
Yes, sir.
Agreed? All right, tell me if it makes sense. All right, so you need a little deeper understanding. So you agree. So right, I'm saying that my vertical velocity is 0, but I'm saying that I'm still moving horizontal. Do you agree?
Your vertical velocity is what, sir?
Vertical velocity is 0. The
Mm-hmm.
vertical velocity is 0. Agreed?
Yes.
Because we're not getting any higher.
Mm-hmm.
That's the maximum height we reach. So we're not climbing in height. So we know that that's the maximum height because the maximum height is not changing. So if the maximum height is not changing anymore, it means that at that point, my vertical velocity is 0. But do we agree that we still have a horizontal velocity?
That's very helpful.
All right. Because if we didn't, what will happen? Let me tell you what will happen. If we didn't, then the motion will look like this. When it reaches maximum height,
It's stuck
yeah,
in the air.
exactly. So it means that you have no further change. So it'd be a dead straight line coming down, which is impossible because of momentum. All right. So that's
Okay.
would have to be something that hit it, all right, for that to happen. All right. So that's just discussing some of the little theoretical things they will ask. All right. So this is an important formula for the motion. All right, for the time. All right. So what we're gonna do, all right. So okay with this part. I'm recording it still, so you can look at the recording on Skype afterwards as well.
Yes.
Yeah. So let's analyze a little bit further and see what we can get at. All right. So for your vertical motion, you know that your initial vertical velocity is u sine theta meters per second. So this is just to remind us, the unit is to remind us that we're talking about velocity. Your acceleration is negative g. meters per second squared, acceleration due to gravity. But what about when the projectile moves up and it comes back down like this? In terms of the displacement, we'll write the formula y is equal to ut, right, plus a half at squared, right? What can we write down in terms?
Why,
Yeah.
why
First,
is it that we can't just use the same thing that we used before?
why? Because what happened now, I'm analyzing different motions, right? So if the projectile move all the way up and all the way down, say we want an expression for the time. Now the displacement y is 0 meters. I remember there's no displacement. So y is 0, so you'd have 0 is equal to u. The initial vertical velocity is just u sine theta times t. Remember, acceleration is negative, so negative g. Of course, we're coming to t squared like that. All right, so that's another expression. So what we have here, look at what we have here. What we have here is what if you want to find the total time? So what is that if you want to find the total, you would have to analyze the vertical motion because it's the vertical velocity that tells us we're in the air. All right. In physics, a vertical velocity allows you to move vertically. A horizontal velocity allows you to move horizontally. So the fact that the projectile is going up and coming down, once I do this, y equals 0, I know that this is going to be my total time that the projectile spent in the air. So what's going to happen now is I write this. Of course, I can factor out a t. All right, so let me get back some space. All right, so the right answer is factor out a t. I don't have to, but let's just do it the mathematical way. It will not affect you because you're not doing any deep maths here, but let's just do it that way. All right, so we're gonna have u sine theta t minus a half gt squared equals 0. So if we factorize, you're gonna have t outside the bracket. Inside the bracket, you're gonna have u sine theta alone now minus a half gt equals 0. So from quadratics, either t is gonna be 0 seconds or u sine theta minus a half gt is equal 0. So now what we're going to do now, we're going to make t the subject of this formula and find the flight time. So u sine theta minus a half gt is equal to 0. We need to find an expression for time. All right, so tell me when you're ready and I'll move again. Okay?
Yes, sir.
All right, so let's find an expression for time. So we are at u sine theta minus a half gt equals 0. Transposing. All right, so I'm going to have u sine theta. Just carry this over the equal sign. Negative a half gt. I'm going to get positive a half gt. I'm just going to multiply both sides by 2 to get rid of the half. I'm going to have 2u sine theta. So 2 times a half is just 1. So 1 is understood to be here, so I don't have to write it. Dividing by g. Divide both sides by g. Therefore, I'm going to have t is equal to 2u sine theta over g, right? Okay,
Okay.
so t is equal to 2 u sine theta over g. Remember, this was what we got for halfway, right?
Yes, sir.
U sine theta over g is what we got for half, right? Half the time, right?
Yes, sir. I don't. Oh, you didn't have the two there.
Yeah, exactly. Because You know what this is now? So if we draw now, so from here to here is u sine theta over g. And then this other half here, the time
Oh,
is u sine theta over g. This is proof that projectile motion is symmetrical. All right, so what I want to do, I don't want to, there's, in unit one, there are hundreds of formulas. All right, so I kind of wanted to kind of have a little appreciation. So I'm gonna give you a question for you to take 5 minutes and do it.
okay, sure.
Based on this. So, all right, so of course, I think you can share your screen as well. So let's do it. All right, so finish here.
Yes, sir.
Okay. So you see that when you add u sine theta g plus another u sine theta g, you will get the two, right?
Yes, sir.
Show that the motion is symmetrical. All right, so show that the motion is symmetrical. All right, so go 5 minutes, and based on what we discussed, you can draw a graph to start you off, just to remind yourself of what symmetrical is, and then now you can go into the mathematics.
Finish the equation, sir.
Okay?
Finish the equation.
Got the same one?
Yeah.
Okay. Once you got the same one, you're good to go. Alright, so this is it, of course.
Got. Yeah.
Not only that,
Is it necessary to put the bracket there? Because the way how I work it out, I have two u sin theta over g. I
yeah,
didn't have the bracket.
the reason for the bracket is to make it obvious that this is 2 times the time for half the motion.
Okay.
That's the only reason. I don't have to put the bracket any at all. I could have just had this, it's the same thing. But in terms of what I want to say to you, it probably will be a little bit more difficult for you to see that. So that's why I just put the bracket.
Okay.
All right. So for half motion, you can tell them that T half will be U sine next half of the motion. Therefore, the force. Huh? So that's how we know it's. All right. So no problem.
Okay.
All right. Perfect. So next, we can talk about the range of the projectile. So again, to calculate the range, we know to consider the horizontal motion. What's the horizontal motion? X is just equal to the horizontal velocity multiplied by the time t. And that's where we can stop. But we know that this t is the total flight time, and we have an expression for uh. So we can say x is equal to uh. Remember, it's just u cos theta multiplied by the flight time. Really, we know what the flight time is. What's the flight time? The flight time is 2 u sine theta.
Over g.
Yeah, so we can say x then is equal to u cos theta. Just write that as a fraction right away. Multiplied by t. Instead of writing t, I'm going to write that t is equal to. It's equal to this. So I'm going to replace t with this term. Right, so multiplying x is going to be equal to u times u. I'm going to have 2u squared. All right. And then I'm going to have sine theta, cos theta all over g. So the range of the projectile can be expressed like this. But there, of course, in mathematics, it's pure elegance. So we're not going to leave it like that. So I'm going to further simplify. For calculation purposes, you can. If they ask you to prove it, they won't ask you to do that because what I'm going to do next is just trigonometry. If they're going to ask you that, they will give you they will give you a relationship for you to use it.
Okay, sir.
All right. So here, what we have here is x is equal to 2u squared sine theta cos theta over g. Of course, we're expecting that gravity is going to affect the range of the projectile again. So here x is going to be equal to 2u squared sine 2a over g. Right? So in mathematics, right, sine of 2 times an angle is just equal to 2 times sine theta cos theta. If they're going to ask you to do that, they would give you this from maths. So that's it. So this is the range of the projectile. And of course, the range is affected by the horizontal velocity, of course. The range is affected by the angle, and the range is affected by gravity. So these three things affect so far projectile. But the maximum range of a projectile occurs when theta is equal to 45 degrees Celsius.
Okay.
All right, so two examples.
Okay, sir.
All right, so I have two questions, so let's have a look at this one. Of course, in this is we'll just use the technology. I'm just going to take a picture. Now let's look at it one by one, and then I'll allow you to just try it, and then we'll have a discussion. Then we'll look at the next one. Allow you to try it, then have a discussion. All right.
Okay, sir.
Send it now.
Um,
Uh-huh.
sir, can you resend it? It's blurry.
Yeah, that's what I. All right, this one should be better.
Yes, sir.
Yeah. So it goes like this. An athlete in the javelin event runs along a horizontal track and launches the javelin at an angle of 40 degrees to the horizontal. So we know we're dealing with projectile motion, right? So he's going to throw something, it's going to move on the gravity, and he's throwing it at an angle. So immediately we know that we'll have a horizontal velocity and a vertical velocity. The javelin rises to a maximum height and then falls to the ground. Sorry, the javelin rises to a maximum height and then falls to the ground level. So it hits the ground 4 seconds after launching. So they are giving me the total time. Alright, total flight time. Alright, so I'm not even concerned with the numbers because I know all the equations to analyze. At a point, a horizontal distance of 75.2 meters from the launch point. They want to see A1 show that the horizontal component of the launch velocity is that, and then calculate the magnitude of the launch velocity.
Okay. Triple horizontal component. Show that the horizontal component of the launch velocity is
All right. G as probably meters per second.
yes, sir. I think I noticed something. You said use 9.8, right, sir?
Yeah, you can use this.
Oh. 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 I think I got it, sir.
Okay.
All I did was for AI, all I did was to just divide the 75.2 meters by the seconds, just 4, and I got 18.8.
Okay, so the horizontal, the range of the projectile is x equal to that times the time, right? Because based on the information, they told you that the flight time was 4 seconds, and they told you that the range is 75 point, right? 2 meters, right? So based on what they give us. So okay, all right, you're good to go. All right, continue. You're on the right track.
Would the answer be 12.1?
12.1. All right, let's see. Well, I kind of just wrote this equation that immediately, all right, the launch velocity, you see that
Sorry, isn't it asking for velocity, not the distance?
let's see what the answer. Calculate the magnitude of the launch velocity. So launch velocity is going to be u. So basically, you have the range already. I don't know what it is though, no, because I didn't calculate it. But you have the range. You know what g is, and you know the angle. So this formula allows you, this expression allows you to quickly get what u is. Right? So if I just transpose, I'd have gx is equal to 2u squared sine 2 theta. And I can then say, okay, u squared is equal to gx over dividing by 2 sine 2 theta. So once I input the numbers, I can calculate the launch velocity u. Because, yeah, they gave us the angle as well. So 2 times that angle. So it's just going to be g 9.81 times the 75.2, 2, and then sine. And when you put sine in the calculator, you'll have to say 2 times 40. So the angle is, you're going to sine the angle 80.
So I only have to put sine 40 there, 2 times sine 40? Okay.
Yeah, or just sine 80.
It's 241.969.
All right, so 241 point.
I got 241.69.
Okay, and then find the square root, find the square root.
Okay. 15.5.
Oh, okay. All right, so that's the launch velocity. That's the launch velocity. All right, so yeah, they didn't ask you much more because then they go ahead and ask you about some question and ask linear motion, then linking it back with this. All right, but I just want to go one step further here. So we're doing projection at an angle. All right, we're doing projection at an angle. So you can use projection at an angle to show that the motion is parabolic as well. So you already have the horizontal motion, x is equal to u cos theta times t. And then now you're going to have the vertical motion. All right, so you're going to have the vertical motion. Y is equal to ut. So what you will need to do now is, these are the two equations. So when we analyze the horizontal motion, we got this. When we analyze the vertical motion, all right, we know that this will be negative in the middle because this is negative, we got this. So if we want to show that projectile motion is again parabolic, we need to make t the subject of the formula. So for the first one, x equal to u cos theta times t, making t the subject. X is going to be equal to u cos theta again. And then now I'm going to substitute this into this equation. So y will be equal to u, instead of writing t, I'm going to write x over u cos theta minus a half g. Instead of writing t again, I'm going to write x over u cos theta. So u and u cancel. So I'm going to have y is equal to u, okay. Okay, let me back up. There are some missing terms. All right, so x is equal to u cos theta times t. And for, right, so this is the, of course, that. For this one now, this is the vertical velocity. So this is where information was lost. So this part is okay. X is equal to, make t the subject of the formula. I'm going to have x over u cos theta. So that part is good. But this, remember, we analyze the vertical motion to get this. So this uv, the vertical velocity, is actually u sine theta. That is what I left off. All right, so that should be u sine theta. So here I should have y is equal to u sine theta. Instead of writing t, I'll write x over u cos theta minus a half g. Instead of writing, I'm going to get x over u cos theta again. Of course, this is all squared. So the u's cancel. So I'm going to have y is equal to sine theta over cos theta to x minus, this part here is just gx squared over, the 2 is outside, u squared cos squared theta. So this is a parabola again because the highest term in the equation is 2. So just for maths, like when you did quadratic, this is a quadratic equation. Quadratics are parabolas. All right, so that's the concept. So that is where that will be left. So leaving it like that is showing that projectile motion at an angle, the motion is also parabolic.
Okay.
All right, so next, all right, so that's the, all right. So before I said that this angle is theta, there is only one time at which we're at maximum height. So there is only one maximum. So analyzing the curve, all right. First thing, analyzing the curve, there is only one maximum. All right. Look at what happens though. You see that this particular time, this is your x position and this is your y position. Notice that at a later time, you are further along the x-axis, but you have the same y value. All right. Notice here again, if at this time particular is this particular time, at this particular time, all right, this is your y value. But notice at another time, at another value of x, you have the same y value. And of course, this is what the equation is telling you. y is, you remember the equation from us, y equal ax squared plus bx plus c equal plus, yeah, right? Remember this one?
Yes, sir.
Where you have two answers,
Yes, sir.
so it's not surprising. So notice that at here, at this point, you have two corresponding values for x for which you would have the same y value, except for one single point, right? So this is why we know that we're talking about parabolas. So when I did math, I did this. This would be a maximum. Your maximum only occurred at one value for x. All right, and then there are other times you have a y value where two different values of x will give the same y value. All right, and this is not unusual. This is not unusual. And let's analyze why and why this is not unusual. Here's the deal. If I throw a stone up, there is going to be a time when it is, say, 4 meters above the ground. And then there's going to be another time again where it is going to be at same, what, 4 meters above the ground. It's going to be at 4 meters above the ground going up and at 4 meters above ground again coming down. All right. So that's I. But this is the earlier time. This is the shorter time. This is the longer time. So the longer time tells me that is when it's coming down again. Shorter time tells me that is just when it is going up. That was when it was going up in the first place. All right. So these are just some things to look out for. All right.
Yes, sir.
All right. So that's the answer. So the other part of that question is just linear motion. And then now they're going to ask you, by considering that part, how would it affect the answer in A1? Okay, good. All right, so these are some English questions, just like how Kate would ask. All right. All right, so that is projectile motion. All right, so that is projectile motion. So in projectile motion, we can use projectile motion to do forensics. All right, just in case you're wondering, that's a tree. All right, and this is a branch from the tree. And hanging from the branch is a monkey. So this is just describing what's happening. So I'm not going to go through the maths in detail, but it's called the monkey and hunter theorem. So you see the monkey is very bright-eyed. So the monkey sees the hunter, and the hunter has his rifle. Right? The hunter, right, did not take a physics course, and the monkey did not take advantage of the hunter's ignorance. So the hunter sees him. The hunter is very, 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 very far away, and the hunter points his rifle at the monkey like this, right? So
Yes,
what
sir.
happens now is that when the hunter is about to squeeze the trigger, what happens is that the monkey, right? You know what the monkey did? The monkey is gonna release. So by the time the hunter squeezes the trigger, the monkey releases his hand. But lo and behold, the monkey is gonna be in trouble. Why is the monkey gonna be in trouble? Because the bullet is not going to travel in this straight line because of gravity. And so what's going to happen is that the bullet is going to be, yes, traveling along that curve, but it's going to start to curve down like this. So the monkey, of course, will be on his way down. So by releasing, the monkey is going to be at a point whereby he just may, just may take a bullet, right? So
Okay.
we can say anything because the gun wasn't pointing at us. But the thing is, if you just stayed here, it will be a high possibility that the bullet will bend and curve under gravity. right? But that's making a lot of assumptions still, because that is assuming that the bullet did not have a high enough velocity to at least burst through and travel like this and start bend. So we can't blame the monkey too much. But that is the thing. So it's called the monkey and hunter theorem. And of course, projectile motion, what is not there. All right, so basically, all right, so that's gone through all the equations. Right?
Pardon, sir?
Gone through all the equations of motion. There are some other motion analysis.
Isn't it the same thing for airplanes, sir?
In an airplane,
Like the way how for example, the way how you say that um, the way how the bullet travels is not necessarily like would follow along the line that you aim. So say for example, a lot of times the airplane would have to like fly over a certain building that it's going in their direction of, or a fence or something. So would they have to like recalculate in order to like not hit that or something like that? I
all right,
don't know. That's not what I'm
okay.
saying.
So I just understand what you're saying. But in the case of an airplane, the airplane has engine. So the airplane is not a projectile. Right? So a
Okay.
projectile is any object that is moving only under the influence of gravity. So it should not have any engine on it. So there are no jet propulsion or no thrusting mechanism whatsoever. So just arbitrarily throwing a pen, the pen is a projectile. Throwing a stone, that's a projectile. The only way the plane becomes a projectile is when, for example, say the pilot shuts off the engine. They say at the instant he shuts off the engine, then no, the plane is gonna be moving under the influence of gravity. That is when it becomes a projectile.
Okay.
Yeah, because what is keeping the plane moving is engines, right? And the reason why the plane is not bending and curving down is because there is an upward force that we're going to be talking about as well. That's called lift. There's going to be an upward force. That lift force is keeping it up. So the plane wings is like this. It's an aerofoil. So when air moves like this, there is air moving like this. All right. So based on the velocity of the air, you all right? The plane wing is shaped. It is shaped so that you have high pressure below the wing and you have low pressure above the wing. Right? This is called aerodynamics, and this is known as spin. So you have high pressure, low pressure. So below the wing, you have low velocity. Above the wing, you have high velocity. All right. So what that means is that you build up high pressure, low pressure here. That is what causes the lift. So that's why the plane accelerates so fast before it can lift off. It is depending on that horizontal speed, that horizontal velocity, to increase this lift force high enough so that it can overcome the weight of the aircraft and lift off. All right. So that's just an idea of airplanes. But the good thing is that there is lift, all right, that we're going to do as well. So we're going to do banking of aircrafts. So we're going to do circular motion and banking. All right. So without further ado, we can talk about that.
Okay.
All right. So that is how aircraft work though. But as it is though, rockets and airplanes, anything with engines, they are not projectile. Projectile is just when things are only moving under the influence of gravity. So if I shut off the engines, now the plane starts. Then that is when it becomes a projectile.
Okay, so
All right. So that is Bernoulli's principle. But Bernoulli's principle is not in your syllabus though. All right.
okay.
So next, all right, so as I said before, there is a lot of overlap in C-secant cape. So the next thing, so after motion, you do Newton's laws and momentum and stuff like that. So what I will do is, I will talk about Newton's 3 laws of motion. They will ask you to state it, but I'm not going to write it. All right, so I'll just make you know that we're going to be doing Newton's 3 laws. I'm going to state all 3 laws. Now, of course, you can just write them homework. They bring back a lot of things that I actually did already. So the next thing, though, we're going to talk about is this. We're going to talk about graphs. So the most is for this. So a ball, it starts from here, falls and hit the ground, and bounce and reach a certain height again, and then fall and hit the ground again. Ball falls, bounce, reach maximum height, fall again, and hit the ground. All right, so just like how the arrow is showing, that is what happens. So the ball is released from rest. So this is the initial velocity, 0 meters per second. So we're going to analyze the motion graphs for that ball. All right. So in terms of a distance time graph, so if you should plot distance versus time, all right, so distance versus time, no problem. Distance is scalar, so start measuring from somewhere. As the ball moves from this point here, A, and moves to the point B, then moves to C, then moves to D, all right, distance increases. So distance is scalar. So I can just draw a straight line, that's A to B, right? That's when it hits ground. Moving to C again. I draw a shorter line. Not gonna go as high. Moving to C. This is now C. I draw a line. So that's just distance. The total distance over all of this time. So if I ask you what is the total distance the ball would have covered over all of this time, that is from when the ball falls from here, from A to B. So this is A, where it starts off. At A, no distance. At B, it covers this distance. At C, it rises back from to this height. And then D, it falls back. So that will be it.
Okay.
But for displacement is up. So it will be so for the displacement from A, all right, so the displacement increases with time. So that's from A to B. What's going to happen now is that from B to C, totally different scenario. From B to C, so the direction changes. All right, so from B, so when the ball bounces from A to B, this is it. From B to C, the direction changes. And so the displacement, of course, increases in the opposite direction. And of course, from reaches, so when it reaches here again, see, of course, it will start move in the opposite direction. So that's the displacement. The displacement is different. So coming like this up here, the positive is for one direction and the negative is for the next direction.
Okay. Plus.
Right? But of course, we're going to go through all of the motion graphs. We're going to go through all of the motion graphs. But before we normally do the motion graphs, I normally do momentum and Newton's laws. So that is what I'm going to do. Because I'm going to have to draw the motion graph for momentum, as I just remembered. I'm going to have to draw the motion graph for acceleration. So I want to do Newton's laws. So let's do Newton's laws. It's because I wasn't going to restate the laws, but we're still going to talk about certain things in Newton's laws. So you have to recall Newton's 3 laws of motion. Newton's first law states that a body will continue in its state of rest, or a straight line, by some external force that applies. They're still going to ask you to state it, but no, this time it's 1 mark. And then they're going to ask you to state Newton's second law. The applied force acting on an object is directly proportional to the object's rate of change of momentum, and the momentum change takes place in the direction of the force. So they'll ask you to state Newton's second law as well. So you can just write that down for homework. Newton's third law: when a body A exerts a force on a body B will in turn exert an equal but opposite force on A. So those are Newton's 3 laws of motion. And the law of motion we're going to be talking about. All right, for next class, we're going to be doing it. We're going to be talking about F equal ma, where F stands for force. Some calculations to do, measured in newtons. M stands for mass, measured in kilograms. And A stands for acceleration. All right, so that's fine. All right, so also, we're going to look at the formula. Power is equal to force times velocity. As and of course, Newton's law now. We're going to have to do the calculation. So this is the long part now. Law of conservation of momentum, but we're going to have to do it in 2D. So in CXC, you did it in 1 dimensions. Here, we're going to do it in 2 dimensions. All right, so we're going to explore Newton's laws and work some examples there, and then we'll do the law of conservation of momentum. First, we're going to do back what we did in 1D, 1-dimensional motion. But then now we're going to have to talk about what's happening in 2-directional motion.
Okay.
All right, so that's next. All right, so that is going to be more heavy calculations again. So that's the idea. So what I want you to actually do is to state Newton's 3 laws of motion for homework. We're just going to use the 3 laws to solve problems, because coming out of Newton's third law is the law of conservation of momentum. And that's what we'll do for next time.
Yes, sir.
All right, so
Thank you for your time.
yeah, no problem. All right, so yeah, so we'll do another hour and a half as well. So state those 3 laws and we'll continue the journey again.
Yes, sir. Have a good night.
Same to you.